Hello, good evening, children. So, I'm going to continue the last lesson, and our main aim is to understand the remainder theorem and the factor theorem, which is very closely related, as we will see now. Okay, so let's start. Let me try to pick up from where we left off last time. So what we said was that if I have a polynomial, and let me take an example, x square minus 5x plus 10, and I divide this polynomial by another polynomial, and let's take a simple example, x minus 1. Now, what will be the remainder? The question that we're going to ask is, what is the remainder? So, notice that we don't seem to be interested in the quotient right now, and the question is, what is the remainder? So, I just want to remind you that the remainder is going to be a polynomial of degree 0, because the divisor here is of degree 1. So, the remainder is of degree 0, and that means that it is some constant, some number into x raised to 0 or some number, okay, where the c is some number, real number. So, what is the remainder? And basically, what the remainder theorem says is that it is very, very easy in this case to find the remainder if the divisor is of degree 1, as it is in this case. And the answer is simply, the answer to this question is that it is simply p of 1. Okay, so once again, if g of x is equal to x minus 1, then it will simply be p of 1. And just to tell you, if g of x is, let's say, x minus 2, then you just have to do p of 2. And I hope you'll all remember what is p of 1. P of 1 is basically you take p of x and then you put x equal to 1. So we have p of x in our example as x square minus 5x plus 10. And now let's do p of 1. That means take the value of this x as 1. And so it becomes 1 square minus 5 into 1 plus 10, which is nothing but 1 minus 5 plus 10, which is nothing but, what is this? 6. Okay, so what we are saying is the remainder is 6. So this was a very easy way to calculate the remainder. Now let me quickly check to see whether we are right. Well, we only know one other way to get the remainder, and that is to do the division, which we did last time. So let's actually do the division. X minus 1, and then we have x square minus 5x plus 10. And so let's do the division. So we have an x here, and then you have x square minus x, and then you do the minus plus, this gets cancelled. We have minus 4x plus 10, which cannot be the remainder because it's still of degree 1, and we need something of degree 0. So we continue, we do minus 4, and then we have minus 4x, and then we have plus 4, and then you do a minus, then you do a minus, and then this becomes plus, this becomes minus, this gets cancelled, and there you go, 10 minus 4 is equal to 6, and the answer is right. So this definitely is a very cool way to get the remainder, very fast, and that is precisely the remainder theorem. Okay, so let us state the remainder theorem. It says that if you have some polynomial p of x and you divide this by g of x, let's say with a linear polynomial, which we'll simply call as x minus a, then this would imply that the remainder is simply, the remainder is simply P of A. And if you divide by, let's say, x plus A, and this would imply that the remainder is P of minus A. And so now it definitely is a very nice theorem, and the proof is very easy. Okay, so let's just write the proof, and you will see that we are very comfortable with all the steps of the proof. Okay, so we say that P of x, when you divide with x minus a, you get a quotient and we get a remainder, which is actually a polynomial, but it's a polynomial of degree 0. So this will actually be equal to some constant times x raised to 0, which is that constant. X raised to 0 is 1. Now, what is the meaning of this is something that we spent a lot of time. So what this means is P of x is equal to the divisor, which is x minus a, into the quotient, which is the q of x, plus the remainder. This is what it means, and this is really the 1 or 2 step proof here. So you start by writing that P of x is equal to x minus a into quotient plus remainder, and now you see this is just one golden step in the proof, and that is that you substitute x equal to a on both sides above, and that is the one single beautiful step for which I mean the whole class 1 and class 2 was just for this one step. You just have to put x equal to a on both sides of the above equation. So when I put x equal to a on the LHS, P of a, and when I put on the RHS x equal to a, I get a minus a into q of a plus the remainder. But here's the magic step. Basically, a minus a is nothing but 0, and now we get P of a is equal to 0 plus r, and that would mean that P of a equal to remainder, and that is the end of the proof, which we normally write as QED. QED means that the proof has ended. So now you can see how for the last quite a few classes we have been constantly saying that the division that you have learned is extremely useful, and the division helps you to give a one-line proof of a very beautiful theorem called the remainder theorem, which is basically that P of a is equal to the remainder if I divide with x minus a. Okay, so let's just do one more example. I have a polynomial P of x is equal to, I'm just making up any polynomial I like. It can be as complicated as you wish, but I'll just take a cubic polynomial, and let's 2x square plus 5x plus 3, and I say that I'm going to divide this by g of x, any linear polynomial. Let's take that as x, x plus 2 for a change, and now we use the remainder theorem, which says that the remainder is simply equal to P of minus 2. So let me put minus 2 in, let's put the value of x equal to minus 2 everywhere, and what do I get? 4 into minus 8 plus 2 into 4 minus 10 plus 3. And so let's evaluate this. I made a mistake. No, I'm fine. Okay, so this is equal to minus 32 plus 8 minus 10 plus 3, which is minus 42 plus 11, and that is equal to minus 31. So here we go, we got an answer, and it is pretty fast. So once again, it should be fine, but if you're not very because we're doing this for the first time, let's actually check this by brute force, and at the same time it will become an important example for us to practice our division. So I'm trying to make some space for myself. So maybe you'll remember that the remainder is minus 31, so I just keep the minus 31 here, and let's use the space for actually carrying out the division. I hope that I'll be able to manage it here. Please note that we are not in a position to calculate the quotient by a shortcut, but only the remainder, and so the quotient is really not important here, and we are trying to see what the remainder is. So let's do it. 4x and square, and then you have 4x cube plus 8x square. You put a minus, and what do you get? Minus 6x square plus 5x plus 3, and then you have minus 6x, then you have minus 6x square minus 12x, and then you put a plus and a plus, and this gets cancelled, and I have 17x plus 3, and this time I have to put plus 17. Remember that 17x plus 3 cannot be the remainder because we're looking for a remainder of degree 0, and I have 17x plus 34, and then I have a minus and a minus, and minus 31. Great. So there it is, minus 31, the remainder. So these were simple examples to convince you that the theorem is working fine, but more importantly, we are given a proof. But now let's also, in the same class, in the same breath, let's also get done with the factor theorem. So here it is. So let's take an example. Suppose that the polynomial, I'm taking a simple example, is x square minus 5x plus 6. And suppose by chance we guess, or we just got lucky and we calculated some number, let's say p of 2. So let's see what is p of 2, and if it happens to be 0 by chance, well, in this case it does happen to be 0. Let us see what is p of 2. P of 2, you just have to put x equal to 2 into this polynomial. So let's do that. 4 minus 5 into 2 plus 6, that is equal to 4 minus 10 plus 6, that is 0. So if p of 2 is 0, implies that x minus 2 is a factor of x square minus 5x plus 6, that is of this polynomial. So, and indeed you can see that this is a very simple example. P of x can be easily factorized, x square minus 5x plus 6, as we can easily factorize this as x minus 2 into x minus 3, and indeed x minus 2 is a factor of p of x. So that is the statement of the factor theorem. So this is, I just took a simple example. In other words, if you get some p of something as 0, then x minus 2 is a factor. Okay, by the way, if p of minus 2 is 0, this would imply that x plus 2 is a factor. Now, interestingly, the proof is almost on the identical lines. So let's do the proof. Okay, how will we write the theorem? Theorem is, if p of a equal to 0, then x minus a is a factor of p of x. So here's proof 1. Okay, and I think this proof is better than any other proof. So we say that let's divide p of x with x minus a. So use the fundamental definition of the division, which says that p of x is equal to quotient of x into x minus a plus the remainder. But now from the remainder theorem, remainder theorem says that the previous remainder theorem is going to be used in this proof, says R is equal to P of A. And now that would, but then we started off by saying that P of A is 0. Okay, it is given that P of A is 0. So P of A is equal to 0, and this would imply that R is equal to 0. Now if R is equal to 0, that means that you can get rid of this term completely, and you have the following statement: P of x is equal to some quotient into x minus a. So P of x is equal to x minus a into something which we are calling q of x, and clearly then these are the two factors, factor 1 and factor 2 of p of x, and that would definitely mean that x minus a is a factor of p of x. Okay, so maybe I'll just end this lesson with another silly example. We all know that x square minus a square is equal to x plus a into x minus a. I'll just take up a silly example like this, or even more specific example: x square minus 4 is equal to x plus 2 and x minus 2. So definitely, now look at, this is the example. We know that these are the factors. This is already well known to you. And now suppose that we start off by saying that p of x is a polynomial which is x square minus 4, and therefore now you watch p of 2. What is p of 2 is 4 minus 4 equal to 0, and that would mean that x, as per the factor theorem, x minus 2 is a factor. And you also see that p of minus 2 is again 4 minus 4 equal to 0, and that would mean that by the factor theorem x plus 2 is a factor. And now you can see that indeed these two are factors. So I hope that you know what the factor theorem is now. And what we'll do is I just want to end by stating clearly what we have achieved. We have stated the remainder theorem first. Why? Because the remainder theorem is also used in the proof of the factor theorem. Okay, so it is better to prove the remainder theorem first. And both of these are very powerful, simple tools, and I'm going to give you lots of examples of the applications of these two theorems in the next class. But right now, I just want to end by reminding you that the only thing that was required was division of polynomials and the basic definition of the division of polynomials, which is that p of x is equal to quotient of x into divisor of x plus the remainder of x. And this understanding was all that was required and was a crucial step in the proof. And so we have learned something very, very useful just because we are good at dividing polynomials and understanding what it means. So please, this is a reminder to you that the things, simple things you're learning in school are very, very, very important. So please, I hope to do the next class tomorrow itself, and I'm going to teach you some applications of those beautiful theorems called the remainder theorem and the factor theorem. I'll state the theorem again and then give you some applications. Thank you, and please stay in touch, give me feedback for the class so that I can improve and reach out to you in a better manner. And once again, I thank all your teachers for helping me to be in touch with you. Thank you very much. Bye.